Part 13. Harmonic Resonance in Motor Control. Let us examine the principles of motor control beginning at the lowest rung of the evolutionary ladder of animals with the lowly paramecium, a single-celled creature that propels itself through the water with wave-like motions of its cilia. Obviously, the synchronized motion is evidence of a wave-like synchronized process in the body of the animal without a single neuron or synapse or nervous system. And yet, this wave-like pattern has an element of intelligent control, because when the paramecium gets stuck in a dead end, it knows enough to reverse its synchronization pattern and to back out of the hole and to turn to a different direction and try something else. This is extraordinary intelligent behavior for a single-celled creature. Here's an actual paramecium swimming through the water. The principles of motor control can also be followed from single-celled to multi-celled organism, beginning with the Chlamydomonas, a single-celled organism equipped with two flagella that it waves in synchrony like a swimmer's breaststroke. This creature is also phototaxic. That means it steers towards the light, unless the light gets too intense, in which case it steers away from the light. The transitional creatures, gonium, Pandorina, Eudorina, and Pleodorina, appear to be successive stages of more and more cells remaining stuck together as if by accident in a failure to separate during cell fission. The Volvox is the most sophisticated organism with a fixed number of cells. In all of these creatures, the flagella wave in synchrony, thus making the little multicellular creatures spin round and round in the water, and yet they are still phototaxic, steering towards the light. And yet there is no nervous system of any sort evident in these creatures. One level up, the hydra has a nervous system. It's a multicelled creature with three layers, endoderm, ectoderm, and mesoderm. And the mesoderm is composed of a very primitive nervous system, much like a fishnet stocking, with primitive synapses that propagate waves in both directions. For example, if you stimulate a hydra at one point, it generates waves of activation like the rings in a pond. And yet, this very simple creature is capable of some sophisticated behavior. For example, when it eats, it contracts its tentacle in the direction of its mouth while extending it in the opposite direction, and it extends its mouth to accept the food. The hydra is also capable of a sophisticated somersault locomotion, whereby it contracts its body in the direction of desired motion and extends it in the opposite direction. Then, when upside down, it reverses the contraction and extension until its foot hits the ground, and then it reverses again to repeat the cycle. An extraordinary pattern of behavior for such a simple nervous system. Here are some animations of hydra locomotion made by animated models based on observed behavior, for example, expansion and contraction. Looping, where it bends over, grabs the ground, skids its foot up closer, and stands up and repeat as necessary. Somersaulting, bends over, grabs the ground, flips its body over its tentacles, plants its foot back on the ground, and stands back up. Repeat as necessary. And look at this, standing on its head and walking like a multi-limbed creature. This is extraordinary behavior for an extremely simple nervous system. Here's a centipede exhibiting periodic waves of motion of its legs. And here's another centipede. Six-legged insects have a number of characteristic gaits, or sequence of moving their legs. And these patterns are sorted in sequence of how energetic the gait is. So the lowest energy ambling pattern that insects exhibit is a pattern where it's the right 3, right 2, right 1. These right legs are advanced in sequence, followed by left 3, left 2, left 1. Here's the left legs advancing in sequence, and so on. Repeat is necessary. Here's another time trace going horizontally, showing right 3, right 2, right 1, alternating with left 3, left 2, left 1, and so forth. If the insect is in a bit more of a hurry, it will start to overlap these. So we have left 1 and right 3, then right 2 and right 1 with left 3. So it's as if you took these and pushed them down to overlap by 1. And here is a double overlap gait that requires even more energy but produces more speed. And then there's the parallel wave gaits, where it goes back and forth between the two sides in yet another higher energy but higher speed gait. And here is the alternating tripods gait, a particularly elegant pattern whereby 3 of the legs, here shown in black, are planted on the ground and don't move, and the other 3, shown here in gray, are advanced forward, alternating with the reverse pattern where the ones that advanced before are now static and the ones that were static are now advanced. So here's the very elegant alternating tripod gait that many insects exhibit. And finally, there's the running gait, the highest energy gait, where you just run left and right as fast as you possibly can. Most six-legged insects can do 1, 2, or 3 of these different gaits, but always in the same sequence, in a compromise between economy cruise and high-energy run. The gaits of a horse exhibit the same kind of periodicity. Here's the ambling gait of a horse walking, starting with right 2, right 1, followed by left 2, left 1, much like the insect, right 2, right 1, left 2, left 1. Here we see the pattern shown in time. Here's the trot, where the front left and rear right alternate with the front right and rear left, a faster kind of motion than the walk. And here's the pace, where you alternate the right front and right rear with the left front and left rear, giving a swaying kind of motion. And here's the canter, where you have left front and right rear alternating in a 3-phase with right front followed by right rear. And finally, there's the gallop, the highest energy of the horse's gaits, where it's rear hoofs, front hoofs, rear hoofs, front hoofs. All of these are periodic patterns suggestive of an oscillatory principle of locomotion. Strogatz and Stewart, 1993, published an article, Coupled Oscillators and Biological Synchronization, whereby the variety of gaits available to two-legged creatures exhibits the patterns of two coupled oscillators, and three-legged creatures, like a man with a cane, with three coupled oscillators, and four-legged creatures exhibit the harmonics of four coupled oscillators. Galistel and von Holst in 1980 performed a number of experiments on centipedes where they plucked off the legs of the centipede and observed how it changed their pattern of locomotion. So, for example, in this case, they plucked off all the legs of the centipede except for four, or all the legs except for four with a spacing in between. And what they observed was that whether it was with a spacing in between or not, the remaining four legs of the centipede exhibited the gaits of a four-legged creature. And this was true even when they amputated a number of intermediate legs, leaving only extremely remote pairs in synchrony with each other. When they amputated legs preserving three pairs of legs, then the insect exhibited the gaits of a six-legged insect, regardless of whether the amputated legs were adjacent or separated by several limbs. That pretty much clinches the case. In the centipede, already generalizes to the pattern of four-legged and six-legged creatures. This is a multi-potential pattern formation principle where a simple mechanism can, with small variations, perform a multitude of different kinds of actions. Here is a bioluminescent jellyfish.
The bioluminescent jellyfish is a truly majestic creature. As they slowly navigate the ocean's currents, small cilia propel them forward into the depths of their watery surroundings. Because they can swim on their own, they are classified as nekton creatures.
Note how their cilia blink in different colors. This is caused by the chemicals lucerafin and luceraphis, which, when triggered, react together and cause a photoprotein to be created. This photoprotein is what gives off the glow, and different proteins create different colors.
You can find bioluminescent jellyfish in any ocean, but they're in the aphotic zone where they don't see the sunlight, and they are most commonly in the oceanic zone, away from the shore by the mid-ocean ridge.
And here is a bioluminescent squid. Observe the patterns on its skin. They are periodic cyclic patterns that are reified on every patch of its skin, and they reflect the patterns of muscular contraction of its locomotion. Here's a snake swimming through the water with periodic undulations under control. So when we observe the sinusoidal motion of a swimming snake or eel, we can see that there are patterns of contraction and extension on alternate sides of the body in a periodic pattern that is cycled through time, creating propulsive waves of undulation. But the eel has steerage control. It can still steer left or right by doing a greater extension on one side of its body and a greater contraction on the other. When this is added to the undulating propulsive activation, this creates propulsive plus steering combined signal, a kind of thing that is done very easily by harmonic resonance. The traditional notion of a motor neuron is the concept that each motor neuron branches to innervate a variable number of muscle fibers. So here is a motor neuron from the spinal cord that goes out into muscle and makes contact at various different points. And the motor unit includes each motor neuron and all the fibers the innervates. The innervation ratio can be up to 1 in 1,000, one neuromuscular junction for each 1,000 skeletal muscles controlled by it. This suggests a blurring of the motor control signal by a factor of 1 in 1,000, creating a less precise pattern of motor control. The alternative concept is a motor unit as a resonator that promotes a particular standing wave pattern in the muscle rather than dictating the exact contraction of each muscle. Part 14, Resonance in Visual Experience.